unless I get an explicit request from you guys to do a particular year, but this question rears its ugly head in a lot of places. So I'm just going to do this because it's a type of digital controller question you get. So that is 2016. So as always, what I like to do, I like to write out the actual control blocks just to give me an idea of what exactly I'm trying to do, and I can organize or structure my thoughts around that. So I'm going to do that. Let me just get that open. Aha, okay, cool. Hope it won't grain as badly today. I tried to play around with some DPI settings. I hope it did the things. Okay. Fine. Somebody remind me, this is
2016.
2016. Thank you. Q5 digital control. Thanks. Okay, so I've got my reference signal coming in here. That's being sampled. Got my digital signal. I mean my digital controller, sorry. ZOH. The plant. That's minus, okay. Okay, adjust that a little bit. Okay, cool. So in A, we need to derive a pulse transfer function for the zero order hold plant combination. So this thing over here. I think I'm gonna say let that equal. Okay, this is still the continuous domain, so I'll leave that for now. So what I'm gonna do is I'm gonna say let insignia S equal zero order hold of S GP of S. Ergo insignia Z is equal to the Z transform of zero order hold of S multiplied by your plant gain. Okay? Insignia Z equal to 1 minus Z to the minus 1. Now using the step invariance, this is what you have. So at this point, you want to focus on GPS over S. This integrating action you have over here, this is going to be equal to S plus 2 all over S squared S plus 1. Okay, cool. Now At this point, we find partial fractions. Okay. S plus 2 squared S plus 1. Okay. Take that to Wolfram. Okay. And that's what we get. Okay. So, whoops. Coming back here, our partial fractions are 2 over S squared plus 1 over S plus 1 minus 1 over S. Now we go use our Z transform standard tables, right? So the Z transform of GPS over S is going to be given by the following.
Could you,
Sorry, Manus, you had a question?
no, I was going to give an answer.
Okay, cool. If you have them, great. But I'm just bringing up my table now. So this is going to be 2 multiplied by ZT all over Z minus 1 squared plus Z all over Z minus E to the minus 1t. Correct. Somebody can just double check that I'm not chatting nuts. Minus Z all over Z minus 1. And from your diagram, you know that t happens to be equal to, what is it, 1 or 0.5?
It's 1. No, it's 0.5. 0.5. 0.5.
Okay, cool, no beefs. Okay. Okay, so t equals 0.5, make that substitution. Over Z minus 1 all squared plus Z all over Z minus, is it 0.367?
Yes. Yes.
Minus Z over Z minus 1. Now you can do the math at this point.
Sorry, Bangz.
Yeah?
It's e to the minus 0.5, right?
Oh, sorry, this is minus 1.
So it's 0.606.
0.606. Okay.
07. 6.
So this is a 7.
Yeah.
Okay. So your LCD is going to be Z minus 1 squared with Z minus 1. Cool. You can do that computation, or you can let Wolfram do it. Do you guys still have access to the pro version of Wolfram, just by the way? Guys?
I'm not
Not
sure how.
sure if we even had access in the first place.
Yeah.
No, that rep assured me you guys did. I mean, no, they were giving tutors Wolfram pro bono, so
Hey,
makes
Bangz,
yeah.
your lowest common denominator is supposed to be z minus 1 squared multiplied by z minus 0.60
What did I put down there? Oh,
minus
sorry,
1.
I wrote that twice. Sorry. Thank you for that catch.
Can I also just ask what happened to the z in the numerator of the first one, of the first term?
That's there. Z, Z, Z.
I think you
Cool.
mistaked it for 2 and you.
Yeah, that's exactly what I did. That is precisely what I did.
It's also something, it said that t is equal to 1, not 0.5 in the diagram, if I'm not mistaken.
It is in fact equal to 1. It is in fact equal to 1. Okay, that's no beef. Three, 6, 0, 7. This is still 2 then. Anything else? No, those are changes.
Our numerator has to change.
Yeah, it's
Denominator.
2Z.
The
Yeah. Okay, that's the form I wanted in, because I already know that it's going to chow with Z minus 1 of the 0 order holds. So that's the Z over Z minus 1 of the 0 order holds. So this is probably the most desirable form you wanted in, because you can already see that you're going to cancel your Z and your Z minus 1 over there. So this is equal to 1.3607 Z squared minus 0. Minus 0.0821 Z. Okay, and you get 1.3607Z minus 0.0821. Okay, Z minus 1, Z minus 0.3607. Okay, now my insignia Z is just going to be given by this 1.3607Z minus 0.0821 all over Z minus 1, Z minus 0.3607. Bam. Therefore, insignia Z, the combination of your open loop and your closed loop must be given by this. Okay. Okay, that's 5A. What's next? Okay, design a digital controller using Kalman's optimum response design procedure to yield a closed loop steady state gain of 13.98 dB. Okay, so now with Kalman's optimum response procedure, you guys remember from yesterday, what is it that we principally have to do? We're trying to get our fudge factor gain, that's a small k, but in so doing, our controller needs to cancel out the zeros of our zero order hold plant combination. Not so? Okay. Guys, am I chatting nuts, telling the truth? All of the above? None of the above?
Honestly, just trying to remember what Kalman's thing is.
It's a design procedure where pretty much I've only ever seen this thing being referenced in that one textbook, Raven. I'm sure there's a paper on it somewhere, but I haven't found it. Okay. So insignia of Z, let's just multiply this out so we can better see the coefficients. So this is 1.360Z minus, what is it? 0.0821 all over Z squared minus 1.3607 plus 0.3607. All right. So anybody, Kalman's optimum response. our first steps here are what? Guys, we know, we remember, we don't know. Should I just go through the straight to the answer? Please let
Do
me
you need
know.
to
Uh,
find? Also, I think DB can go.
I don't continue,
Sorry.
minus.
No, it's fine.
I think the first step is to find G of S.
Okay, cool. That's equivalent to my insignia base. Done. Found. Now what?
We
What is your
need to
principal
find.
aim here?
Our principal aim is to find D of Z.
Mm-hmm.
So the next step should be to find small k.
Cool. Now, how would you find small k? Because remember, we've got now a closed loop, well, our zero order hold plant combination. This is equivalent to your insignia of S, right? So with Prof van Wyck's nomenclature, this is what you have. Now, with Kalman's optimum response, you have something special that takes place when you say d of z multiplied by insignia z, or if you prefer, d of z multiplied by g of z, right? What ends up happening is d of z insignia of z is completely then, what did you use? Q1. Just get this right. No, you didn't use Q, you used P. It's completely characterized by this over here. This is a really key result, guys, because this results in you ultimately obtaining that FIR response. I don't think it's in this past paper, but in one of the questions that I did see, they asked why, given the poles and zeros, is this actual optimal response? Why does it have such good performance? And that speaks, ladies and gentlemen, to the fact that when you put this in closed loop configuration, you actually end up with an FIR filter, i.e. you only have zeros, no poles. Okay, so as BB said, our first step here then is to find that gain or the fudge factor. So going back to the question, we are told to design the controller such that we have a closed loop steady state gain of 13.98 dB. Okay, so just applying the formula. Do you want me to stick with K, or can I change the variable big K? Okay, I'll call it case of noughts.
I think
Q1.
initially what was a bit confusing for me is the G of S part, that they actually meant G of Z.
Yeah, so you see, you just have to watch your domains very, very carefully to understand which domain you are actually operating in. Okay? And Prof van Wyk, I think, swaps closed loop and zero order hold plant combination. He uses them sometimes interchangeably in his notation. I typically tend to use G's for forward, and then if I'm going in the other direction, I would use insignia to indicate, okay, this is just a portion of my transfer function. So let me show you what I'm talking about. What I would prefer to say is, I'd call this insignia of S, and I'd call my entire forward path G of S. That's what I would do.
Question, Banks.
Yep.
Our d of z, could it be multiple functions? Does that make sense?
Multiple functions, yeah, but the thing is, they all have to have the specific characteristic that they cancel out or they chow your actual, they actually chow your poles here for your closed loop pulse combination. So you can have whatever you want. Okay, let me actually just expand this out. Whoops. Okay, while we're here, let's just actually compute what, okay, no, let me actually expand this out. Use this as a teaching moment. So, the actual crux of Kalman's optimum design, right, is that when you design your controller here, okay, I'll just use D, you can have essentially almost whatever you want for your poles, but your zeros need to be such that they cancel out the zeros of your zero order hold plant combination. In other words, this thing that we did yesterday, Q1 z minus 1 plus Q2 z minus 2, that here is just going to be P1 z minus 1 plus P2 z minus 2. Here is 1 minus P1 z minus 1. No, it's minus, whoops. Minus P2 z minus 2. And then down here you've got Q naught z minus 1, Q2 z minus 2. Okay? So the crux of this whole thing is that this thing here, that guy there and that guy there are going to completely specify what your controller needs to be. So now this here and that there can be almost whatever, almost anything you like. The whole thing with your actual digital controller is that it must be such that when we do the multiplication, this completely chows out that, such that our entire open loop response is only governed by P1 and P2, which would be in essence the zeros of our zero order hold plant combination. Well, the coefficients of our zeros there. Does that make sense? Well, I don't know how it can, because I don't know if you guys did the proper derivation. I tracked it down in Raven last night and it's quite in depth. So it's a shame. But anyway, that's what Kalman is. Yeah.
I guess so. Basically, anything that isn't our G plant and our zero order holds, and if you multiply all of those together, that multiplied with our G of Z should give us the, like, this Kalman's thing.
Yeah.
Okay.
Yeah.
Okay, that makes sense.
Cool. Makes sense. Okay. Can we proceed?
Just to clarify, so technically the G of Z is our system, which is the zero order hold and the plant, and then G of Z is the controller. So all together they make up G of S, which is the open loop.
Yeah, you see, this is now the way this notation is. So I'm gonna erase what I've done here in order to avoid confusion. But you are correct in exactly the way you said it, BB. So look, what Prof van Wyk has termed G of S is this here, right? Personally, because I know that's not the complete open loop, I call that insignia of S. That's just me. He calls it G of S. Now, your entire open loop is given by this here. Now, this is then D of S, G of S, right? Okay, so now what Kalman's optimum design or optimum response design is saying is that this open loop, right? Your controller will be whatever it needs to be such that this open loop is completely only governed by the zeros that you had in this zero order hold plant combination. And those zeros are the coefficients P1 and P2. These coefficients P1 and P2, can you see this entire open loop response is only governed by P1 and P2? That's because our digital controller is designed such that, okay, I wrote that further down, such that its actual zeros chow or cancel the poles of your zero order hold plant combination completely. And then the poles of your controller are given by its 1 minus P1, Z1, and P2 there. So this entire thing is only governed by P1 and P2. So that's why I said the nomenclature for me was a bit confusing, even when I initially saw your notes, because I'm of the belief I take G to be my entire open loop, but I had to find out that no. Prof van Wyk was only talking about this portion here.
Okay, thank you. That makes sense now.
Okay, cool. So now we've calculated, did we calculate our K? Okay, now we can calculate it now. So in the question, we're told that we need a closed loop steady state gain of 13.98 dB. Now, for reasons shown yesterday, we know that the fudge factor gain we need is equal to K naught, which is the closed loop steady state gain, over the coefficient of our first delay, i.e. Z minus 1, plus the coefficient of our second delay, Z minus 2. So now that's 13.98 dBs. Doing that quick conversion, shout out signals to A. Now what's our P1 and P2? Oops. This is P1. This guy there is P2. Very important, guys, to take heed of the P1 plus P2. Yes, Mukela?
When you're simplifying from having 1.3607 open bracket Z minus 0.821, did you multiply your 0.0821 by 1.306?
Did I multiply this by? Oh, you
When you
mean
were
here? Oh, so you're saying I didn't multiply? Okay, no, we'll check that again. I'm pretty sure we did, but okay, let's put that form in again. 1 over Z squared minus there's a point here. This is 3.607. 0.607. Okay, cool. Let's try that. So, Michaela, what is your query? You're saying there's a problem with my last term, that constant.
Yeah. I was just asking if you multiplied it, because on my side, well, I have something different, so I just wanted to know if I'm the one who made a mistake and copied
No,
wrong.
okay. Well, we did the maths in Wolfram. Now, unfortunately, garbage in, garbage out. So let's just check this again. But I'm pretty sure we looked at it. So here, you're saying, did I multiply this guy? But it's multiplied here.
Okay,
It's
now I
multiplied here.
actually took the
Yeah.
first one instead of the second. The one you copied. Sorry about that.
Okay, no problem. Everybody else, do you concur with my answer, or do you have something different? Okay, guys, please also note this thing can trip you up, that this is a plus here. It's not a minus. Down there, it's minus P1 and minus P2. Okay. So P1 we said to be what? 1.360. And then this is minus 0.0821. Minus 0.0821. Okay. Somebody put that into the calculator for me, or Wolfram, whatever your poison.
I get 3.913.
3.913.
913.
Okay, cool. So now, good people, we actually need to multiply by this fudge factor game. Okay. Now here's where I saw something in Prof Van Veek's notes, which I don't agree with all the way. I don't agree with this all the way. So Prof Van Veek now, well, I'll just walk you through my rationale here. The whole reason we're calculating this fudge factor gain is that we realize with this optimum design method that we have, Comet's optimum response design, if we do it like this, we won't actually hit a particular steady state gain that we want. Hence, we need to multiply by this fudge factor to get the particular steady state gain that we want. So what I'm going to basically be doing is multiplying this guy here. Wait. Yes, indeed. I'm going to be multiplying this guy here by my fudge factor gain. Now, I saw in your notes, sigma z is equal to k p1 z minus 1 plus p2 right? Prof Van Veek does that. If you multiply that gain, the numerator and the denominator, have you really added or have you really changed the gain at all? I'm asking, not telling now. Would that gain change?
No.
Not really, because you're just multiplying by a factor of 1.
You're multiplying by a factor of 1. So in essence, what you're saying is that gain is fine. Because the check that you use later on with the values of P1 and P2 is still going to be valid if you only multiply the numerator. So I personally think that that's an errata or a typo in the notes, personally, because if you're going to adjust steady state gain, you have to multiply by an outright gain. You cannot adjust gain by multiplying by a factor of 1. Mathematically, that won't fly. That cannot fly mathematically. You cannot get something cannot get bigger multiplying it by 1. So I just wanted to bring that to your attention. I do believe that there is an errata there, an error. Okay, so 3.913. Somebody just help me out, call out what those values were. I don't think I divided by Z at this point yet. Whoops, there's a Z that I'm missing here. Minus 0. That's plus 3607. Okay. 0.0821. Can I just divide through by the Z squared, or do you guys want me to show that step? I do think it's...
You can divide by the Z one time.
Okay. Thank you. Can somebody tell me what the last coefficient here was?
0.0821.
0.0821. Thank you. Then the denominator, that should be 1 minus 1.368 z minus 1 plus 0.368 z minus 2. Okay. So now multiplying by that factor, what do we get? Can somebody just check? I'm just going to write this out. 3.913. 1.368 minus 0.0. In fact, I don't have. Can somebody tell me what the numerator is? I don't have my calculator on me, unfortunately.
I get 5.353 Z to the minus 1.
5.353 z to the minus 1. Yeah.
And minus 0.321 Z to the minus 2.
Minus 0.321 z to the minus 2. Okay. It's 1.368 z to the minus 1 plus 0.3687 z to the minus 2. Correct? Now, if you want to know what your controller is, your controller is just going to be that guy in my numerator over 1 minus this guy over there. So d of z will then be 1 minus 1.368 z minus 1 plus 0.368 z minus 2 all over 1 minus 5.3537 minus 1 plus 0.321 z squared. Okay. Is that fine? Now the check that gets done for, okay, are you still at your steady state gain? What you would then do is you'd say, okay, this is Q5C what? We're still doing 2016. Okay. The check that you do there is you'd say K is equal to, what is that, 5.353 353 minus 0.321 must be approximately equal to the 13.98 over 20. Is that true?
Bangz, why did we flip it?
Sorry, why I flipped it here.
Yeah.
Okay, let me go back up. So, oh, it's not flipped completely. Okay, thank you. Thank you for that. It's just this becomes your numerator and then this becomes 1 minus P. Yeah, but did I not do that? This here went up there and then this became 1 minus that guy over there. Wait. Yeah, this is my plant closed loop combination, which is this over here, right? That's this guy over there. Now, the poles here need to be cancelled out by the poles, well, the zeros of this guy, and then it's 1 minus this, such that when I say this multiplied by that over here, this would chow with that, and I'll just be left with this here over that there. Is that correct?
Okay, yeah, I think I see it now.
Yeah? Cool story?
Yes, thank you.
Because like I said, I do not see the rationale in you multiplying that by 3.913 as well. To me, that doesn't make sense. You're not changing that gain at all. Okay, so then I think the last thing in the question, it asks for you to get the time domain difference equation, and that's pretty simple. You can stick with Prof van Wyck's nomenclature, but if you used any other variables, I don't think it'd penalize you.
Sorry, Bangs, what K is this one now? Is it the same K as before?
This is, yeah, this is, wait. What am I saying? So, okay. How does this relationship go? It goes, pizza, whoops. So, small k, P1, P2 must equal K naught. So P1, thank you for that, P2 must equal K naught over small k. So 5.353 minus 0.321 must be approximately equal to 10, 13.98. Thank you for that. Over, what did we say this was? 3.913. I do not have a calculator with me, but if somebody could please put that into Wolfram, I'd be ever so grateful.
Sorry, Bangs, are we doing, is this supposed to be 10 raised to the power of 13,98 divided by 20?
Sorry, could you just repeat that?
For the 13,98, no, you go down.
Yeah?
Yeah, the 13,98, is that supposed to be divided by 20?
It is indeed. It is indeed. I wrote that. I don't know what happened,
Okay.
but yeah, that's the
Well,
one.
then, in that case, so the left-hand side is going to equal to 5,032, and then the right-hand side ends up being 1,278.
No, that's
if we
wild.
divide by 3.913. But if you
That's-
don't, then it's equal to 5.
Okay, let me just check my notes here. But I'm pretty sure that that's what it is. K multiplied by P1 plus P2 is equal to big K.
Wait, guys, isn't P1 and P2 supposed to be 1,36, and then P2 is supposed to be 0,0821?
So what are you saying that I put in here?
Because what you put in there, isn't that when you multiplied it by the 3,91 something?
Thank you. Thank you. I used the gain value. Apologies. Okay. And I even wrote it in a different color to remind myself. Nice catch.
But in his notes, does he not use the gain values for his
Yeah, but you see, like I'm saying, if you want to do it as per his notes, okay. But I'm saying to you intuitively, if you multiply by k over k, have you changed anything? Unless I've got this, unless I've got my wires crossed and P1 and P2 are down here. Because that's the only time I'd say, okay, cool, you multiply by that gain. But if not, I don't see how you actually affect or change the closed loop gain if you multiply by k over k here. Because that's 1. Yeah, because if I just say this plus this gives me 5. This plus this gives me 5, right? But even in his notes, the verification is it. What lecture is that?
Lecture 13, slide 52.
Okay, fine. Let's go here.
53.
Let's go here. Like I saw it, but I went my own path with Kalman's optimum response. Oops. Have I gone too far down? Nope. Not far down enough, it seems. So here. Right? You calculate that, that's your gain. This, to me, is sus. I don't understand why you're saying k in your numerator and k in your denominator. To me, that is sus. Like, real talk. Then, fine, you flip it. So if you add these guys up, I get 5. Well, I get approximately 5, right? But P1 plus P2, oh, that's not equal. Okay, I see my mistake. I said P1 plus P2 is equal to small k. It's not. It's equal to your steady state gain. Okay, in that case, it still verifies. That's the conclusion that I came to when I was actually doing the problem. So my mistake was I said this. See, I think it's those damn k's. If you just used another variable, I said that, whereas it's defined as this. Okay. So if you say, what did we have? 5.35 for our P1? Well, with the gained values anyway.
5.353 and minus 0.321.
5.353 and
minus 0.321.
0.321. Okay. Are we saying that's approximately equal to 10.13.98 divided by 20? What is that?
That's 5.
That's
It's
5.
5.
It's 5 exactly. Yeah, okay. So
Oh,
I did
the one on the right hand side, yes. The one on the left is 5,032.
5,032. So did we do something with our rounding somewhere?
Probably. Is it supposed to be like equal exactly or approximately?
Look, I said approx because I don't know what we did here. Remember, I put this into Wolfram and I truncated some things.
I think we just made a mistake with the numerator value because you said like 1.368 where we had 1.3607. So yeah, could be there.
You think it's here? Okay, let's verify that quickly. I don't think we did, but fine.
Because you said 1.3607 on the numerator Z. And then when we went down, then it changed to 1.368.
Oh,
Yeah.
rainbows. I see what you're saying. I see what you're saying. Oh, pizza.
But
So
it's
if we make
about
this,
equal. So.
yeah, it's about equal, but it should be equal. Like if it's approximately like you can be out maybe by like 1 sig fig here or there, but 5.03, yeah, that's still a little bit. That's still a little bit more. So
Well,
yeah,
we're off by two decimal places because it's this one here is 5.0003 and ours is 5.03. It's probably because of that 07
yeah,
and 8.
it's definitely because of that. Okay, do you want us to go back and fix it? Like I don't mind, but I do feel you have the procedure. So the essence of what I wanted to illustrate with this, guys, is that this business of multiplying k in the numerator and the denominator, it does not affect this verification at all. You can still verify the gain being this 10.13.98 over 20 without multiplying the k in the denominator. So in class, I know most of us didn't attend, but Manus, did he say anything about why he's multiplying k in the denominator? Because to me, that does not make sense. That doesn't track.
It didn't do lecture 13. And I think this
So
stuff is in lecture 13, and I think it's in the grayed out area. And I think when he was telling me about the grayed out area, he was saying that it's like for extra information. But now I'm not sure because I have trust issues with him. But because like in our notes, it's gray. I think it's grayed out, right?
It is grayed out, but we can just assume that we have to learn everything since he gave it to us anyway.
That's
Okay.
true.
yeah, so that's the thing, because it also appears in a lot of past papers. So I figured, you know what, it's better we just do it. So last but not least, I don't know if you want me to write this out. We can. So you're saying, BB, the issue is here. This should be minus 1.360 something.
Yeah, but it's okay. I think we can all just make a note to go and change it ourselves because it's a small. Like I said, we're off by 2 decimal places.
Okay.
So that's okay.
So D of Z is equal to M of Z, E of Z, right? So this is the next question. I believe the last one is 5. Is it D?
C,
Okay, gosh.
where we have to derive the time domain difference equation.
Okay, cool. So then this becomes e to the z, whatever the numerator was, is equal to mz, whatever the denominator was. Okay? You guys still hear me? No?
What
Yeah,
is
we can hear
M
you.
and what is E?
So this comes from Prof. van Wyck's nomenclature. Like I said, you could use any variables you want, but E, in the classical control sense, is representative of your error signal. Your error signal here. And then M, he just calls this point here. M, he just calls that there. That's pretty much what I'm saying.
Would the N and D for the D of Z be the numerator and the denominator?
Correct.
Or-
Correct.
Yeah.
Correct. I'm just saying numerator and denominator. So that, okay, can somebody read out to me what our numerator is? Or do I need to scroll up? I can. Just gonna take a little while. 1 minus, okay, no, I'm just even going to, can I go straight to time domain difference, or do you want me to write this out first?
I can read it out for you so you can just write
Okay.
it out one time.
Cool, fine.
1 minus 1.368 z to the minus 1.
1 minus 1 point.
368 z to the minus 1
Yeah,
plus 0.368 z to the minus 2.
correct.
Then it's 1 minus 5.353 z to the minus 1
Yep,
plus 0.321.
3, 2, 1, z to the minus 2. Cool. Let's take the difference. So taking inverse z, okay, you end up with e to the n minus 1.368 e to the n minus 1 plus 0.368 e to the n minus 2, that is equal to m n minus 5.353 m to the n minus 1 plus 0.3218 m to the minus n minus 2. Rearranging to solve for m to the n, that's equal to all of that. All of this basically just gets shoved the other side. So that's e to the n plus okay, let me do all the e's first. Minus 1.368 e to the n minus 1 plus 0.368 e to the n minus 2 plus 5.353 m n to the minus 1 plus 0.3218.
I think it's minus 0.3218.
Yeah, I just realized that. Thank you. Minus m n minus 2. Okay, and that's your difference equation. Now, I did make that tiny numerical error there. So I think if you are going to use Wolfram to do the maths, I just used it for speed. Please just double check what you're putting in there. So what I suggest is you do like what I'm doing. Have a little notepad file where I write certain pertinent things down. And then from there, I know I have my Wolfram command that I can go back to and check. Yeah. Okay, so that's 2016. Do you guys want to break now, or do you want to move on to 2018? Because what I'd like to do is finish off 2018. That's the last digital controller type question. So the first one's what we did yesterday, where it's just a sort of straight up digital controller design. Then this is the one with Kalman's optimum response, and then there's one more that I've seen in 2018, which is a bit different. That's why I would like to do it. And looking at the location, if it's 30 marks, then yeah, he could bring different. So
I think we can take a short break now and then come back and do 2018.
okay. So I'm going to finish off that, and then I want to move on to the root locus, because I want to at least get that and the root locus done in this session, because I think compensator design and Nyquist, I've only really seen one question. Like it's always almost in that similar vein. So Nyquist will be quick, hopefully. I don't know if you guys want a story time for those stability plots, but if not, then that'll be quick. And then we can hopefully do modeling, and then so compensated design, Nyquist, and then I think modeling, and then block diagrams will just finish off the next time by itself, or whatever we don't finish off it'll spill over into the next day. But I want to get root locus done today as well. Okay, so we can take a break. I don't mind.